Hey guys, welcome back. Another episode, Healthy Design. Today we'll continue talking about insulin resistance, and we're going to move into kind of insulin resistance and cancer. So I've got to give some background information on cancer and things. So hopefully that will help everything to make sense. But also hopefully I won't go down too many tangents and rabbit holes and kind of get everything lost or make it confusing. I can't remember though if I've said this before, but definitely the idea for how to kind of do these videos regarding insulin resistance comes from Dr. Ben Bickman's book, Why We Get Sick. And so some of the information comes from there directly. There's other sources of information in different videos too. Probably not in all, but in some. And so I just want to be sure. But I like the way he classifies things like part one, part two. So we'll kind of go through all the different systems, how it can play a role, what causes it, and then what to do about it. I like that breakdown. I think it's a good book, so I recommend it. So I want you guys to know. But like I said, it's a very good book. It doesn't cover everything 100% in depth because if it did, the book would be so massive and nobody would ever read it. So let's talk a little bit about cancer. I think everyone agrees, like all the experts agree that what cancer is, it's dysregulated cell growth. So it's just this cell growth that keeps going nonstop and it's not controlled. And that's not what we want. We do want cell growth at times, but we also need cell death at times, and we need those systems to kind of work together in our body for it to function well. Where people differ is what causes that dysregulated cell growth. So we have different theories, just like with everything else. So some people believe in the mutation theory. Others believe in more of a mitochondrial metabolic disorder that's leading to things. I will be upfront and say that's more so what I'm in agreement with, just based on the evidence. And so part of what happened, and so part of the reason why I think that, we had, before the human genome was mapped, it was theorized that once we know the genome, we can cure any disease. And that just hasn't been the case. We haven't seen a slowdown in diseases or anything either since the genome's been mapped. And part of that, I think, makes sense. It's just way too complicated. Um, for example, like one gene mutation, SNP, single nucleotide polymorphism, that was real popular. I don't know, at least when I was hearing a whole lot more about it, it was probably like 5 or 10 years ago. I don't hear as much about it now, but it's still there. And it's this MTHFR mutation. The abbreviation is pretty ironic because a lot of people that have this mutation will end up saying, Mother, you get it. But so what this does, it can lead to a issue with methylation, and methylation is an important process in our body. And so B vitamins can be methyl donors. So sometimes you get this depletion of B vitamins for people that have that SNP. And so it was theorized that, oh, we just need to give them high doses of B vitamins. That way we kind of override that. We have enough methyl donors, everything goes well. And then as we kind of learn more about it, is that, well, no, you don't necessarily need to give these super high doses of B vitamins. And so what it boils down to is MTHFR is not the only gene that has anything to do with methylation. There are others, COMT, and then we have other genes that will upregulate this one will downregulate that one. So there's all these different combinations and how things could interact. I don't know that we'll ever understand how all those possible scenarios can play out. So I think that's why we're not seeing this huge reduction just because we have the genome now. One other thing too, so one of the people I really like listening to in regards to cancer is Dr. Thomas Seyfried, and he's at Boston College, and he's been doing a lot of research on this, and he did research with epilepsy and different things too. And so what they found, while he was studying that, is there were different genes that were associated with epilepsy, but you don't always see mutations in those genes for people that have epilepsy. You could have epilepsy for a viral reason and whatnot. And they also found that some of the treatment, ketogenic diet, calorie restriction, treated the epilepsy no matter what the cause was. So again, to me, that kind of shows that the mutation part is not the biggest driver or the biggest issue. Um, let's see. So we've seen this before where we have these competing hypotheses. We saw it in the distant past when we had the Earth-centered model, and now we know that all the planets rotate around the sun. And then we saw this with the cholesterol hypothesis. We had different competing hypotheses, and one wins out. Sometimes that's based on who has more power, who's more charismatic, or just other factors are involved. We've seen this in the very recent past too, just a couple years ago, but that's enough about that. But going back to the cholesterol hypothesis, what we see is that when we want to think science is this like pure endeavor, and that people will keep it pure, and that they're just going to test their hypothesis, and when that doesn't work, they'll change it, or if they keep getting information to support it, they'll stick with it. But people are people, and we want to be right. And so I can see why sometimes people be like, okay, I think it's this. They find some information that goes against that, so they try to modify their hypothesis a little bit. And so, like with cholesterol, it was saturated fat, then it wasn't that, then it's cholesterol, then it's the like cholesterol number, well, it's the cholesterol particles, well, it's LPA. You just, the hypothesis has to keep getting more and more elaborate to take into account all these different things, rather than just saying like, wait a minute, is there another hypothesis that explains these things and explains them simply? I think in general, all these processes are extremely complex. I think we talked about in the chronic pain episode that, like all the different combinations for how the neurons can fire with each other and the pattern, different things. This is like more numerous than the stars in the sky. I think we're going to have similar kind of things with all the genes and stuff. It's just this huge number that we can't possibly control. And so, yes, all of that is extremely complex, but you should be able to describe things simply. If your explanation for it is just as complex as all those different processes, you probably don't have the right explanation. At least that's my thought on things. So some other things that we see with this, there are different studies where they've shown like there are cancers, so there are tumors where there are no mutations present, and then you have other cancers where like there's all kinds of mutations in the cells in that cancer, in that tumor. And so again, sometimes we see this, sometimes we don't. And so if we're not seeing the mutations that are supposed to be it, then that can't be the cause. Plus sometimes we see those mutations in healthy cells that aren't cancerous. So again, that's just not a valid explanation in my eyes. There's got to be something else better. Again, that's where that mitochondrial metabolic dysfunction comes in. I don't want to go down that path too much because that's not taking us down the insulin resistance, and that's primarily what we're trying to talk about here. But just suffice it to say that the mitochondria seem to be what's involved, and Otto Warburg, figured some of this out like in the 1930s, and this was one of those competing hypotheses. And so when a cancer cell cannot produce energy through oxidative phosphorylation. That's kind of like what I'm doing right now at rest. I'm using oxygen to produce energy. And so cancer cells will tend to ferment. And so they have different substrates they'll ferment, glucose being one of those. So we can see how that starts to tie in maybe a little bit to the insulin resistant side. And then glutamine's another one that I don't think a lot of, at least normal general population people know about. So just a quick aside there. This is where, again, we got to be careful with saying things are good, saying things are bad. Glutamine is the most abundant amino acid in our body. It plays a role in our gut health, plays a role in our immune function. So it's very, very important. But here we see, like, if we have some other disorder going on, like cancer, we probably don't want to be supplementing with glutamine, because now we're providing a substrate that cancer can use to produce energy, which then means it's going to grow. And so we don't want to do that. So again, it's not as easy as saying, oh, this is always good, this is always bad. This is where that nuance and context comes into play, and we have to keep those things in mind. All right, so hopefully that's enough of a background on cancer without getting too complicated. I've got my outline in case you're wondering what that was at the bottom of the screen. So let's talk about breast cancer. this is one of the most common forms of cancer that is associated with insulin resistance. And I think a lot of people believe that breast cancer is associated with the gene mutation, the BRCA. And there is an association there, but just because you have that mutation, that does not guarantee you will develop cancer. So for that, it looks like your percent chance of developing cancer if you have that mutation, it varies depending on what you look at. So it does look like somewhere between 45% to 85% you have a chance of developing cancer if you have one of those mutations in BRCA. So either way, that means there's a 15% group that does not develop that cancer despite having that mutation, up to 55% don't develop the cancer even though they have that mutation. So again, the mutation itself is not the cause. It doesn't guarantee that there's going to be cancer as a result. Where we see insulin playing a role in this is that when you have breast cancer, so one other, I guess, a little backtrack again. Cancer is pretty amazing in what it can do to try to make itself grow. So like I said, it's not able to get energy through the normal pathways, oxidative phosphorylation. So it came up with other pathways to produce energy, and that way that growth just keeps going without being controlled. It'll also do different things to bring in blood vessels to get nutrients so it can grow even more. So, it's very smart, I guess you could say, in that sense. And so where insulin resistance can play a role in all of this is that insulin, remember, it's a growth factor, or it's going to signal and get things to grow. And so what the breast cancer will do is that it will actually have up to 6 times more insulin receptors on those tumor cells than a normal cell. So that means it's going to be 6 times, more sensitive to insulin and pulling that in, and having that insulin around, it's going to really respond to it. So there have been some studies where they used insulin sensitizing medications for people with breast cancer, and it did show some improvement in the disease. Not saying it cured it, not saying it took everything away, but it did help. And so if those drugs are making you more sensitive to insulin, that means there's less insulin floating around, so there's less that can attach to all those receptors on those tumor cells. So that's how it kind of works. One other thing with this too, and again, kind of going against that mutation theory, there was a study done where they took like a cancer cell. So they, again, if it's coming from this mutation, it's going to be the nucleus of the cell that's the problem. And so you've got this nucleus in that cancer cell that has got all these mutations in it. And so they would take that nucleus out and put it into a healthy cell. And guess what? The cell was healthy. So that abnormal nucleus can maintain normal function of the cell, at least up to a point. But when they took like the nucleus from a good cell, put it into a cancerous cell, then that nucleus was cancerous. So it's not the nucleus that's controlling anything. There's definitely something else. And again, in my case, I believe that it's the mitochondria that's helping to kind of control things along those lines. What I do think happens, and this seems to be what the research supports, and again, listen to Dr. Thomas Seyfried, I think he discusses things well, is that I'm not saying we don't see these mutations. We do. There's no doubt about it. The question becomes, what's the cause? I'm not trying to say there's no mutations that occur. That's not it. No, the mutations are there a lot of times. They're not always there, but I do think these mutations are a downstream effect of that dysfunctional mitochondria. As we talked about with CDR, we have these different times where we need feast and we need famine, and that seems to be what helps us to be healthy. That's what helped us to survive for as long as we have, because we had that metabolic flexibility to be able to produce energy in different ways. And so that's a sign of health, and that's why I think we want to make sure we keep our mitochondria healthy. That's why we do want to have times where we're eating a lot and enjoying things, and then times where we're not eating as much. And so that way we can kind of mimic some of these things, because the environment we live in today, food is abundant for the vast majority of us. I understand that's not the case for everyone all around the world, but compared to past human history, food is so much more abundant now than it ever has been. And I just don't think our bodies are made to have that overabundance of energy all the time. So moving back on to insulin resistance and cancer, prostate cancer, we see a kind of similar thing, that there is this association with insulin resistance. Um, if you're insulin resistant, you're 250% more likely to develop prostate cancer. So that means 2.5 times more likely. Again, doesn't mean that insulin resistance is the cause. It just means it's this contributing factor, contributing risk factor. With the prostate cancer as well, we'll see where those cells will actually increase the insulin receptors too. So similar to the breast cancer cells. Um, and then colorectal cancer is another one. What we can see with that is that insulin can lead to growth on the outermost layer of the intestines. So again, if we're getting this unregulated growth, and that could, that's one of the things that we see with cancers, that dysregulated growth. And again, just with insulin being a growth signal, it's an anabolic, it's going to lead to things. So the more insulin we have floating around, if we do have cancer cells there, they're going to probably get that, and it's going to help them to grow more and more. And so that's why we want to try to limit these things. Again, it's not that insulin is causing the issue, it's that once there's an issue there, insulin kind of is magnifying it. And so that's why we want to try to figure out what can we do to lower our levels of insulin. What can we do to try to be healthy? What can we do to make our mitochondria healthy? And we definitely know that exercise is a good thing. Our diet plays a big role, things we're exposed to. And so that's kind of the last thing I want to touch on. And I think this will help explain some of those differences we were seeing with, okay, we got this gene here, this mutation that says we're more susceptible to this. So how come some people display it, some people don't? Genes don't explain everything. So epigenetics definitely plays a part in things too. And so what genes are our genes. And so if we have these SNPs or these things, we could be more likely to express something. But again, like I said, we have this one group of genes, so MTHFR, that's involved in methylation, but they're not the only genes involved in methylation. There's others. And then there's others that will suppress that, others that will exacerbate that. And so we don't know all those different things for everything, and we don't know how all that plays in together. But if we have that mutation, then there probably is this susceptibility to that, to developing that disease. In this case, we'll say cancer. So we'll take the breast cancer, BRCA. You got that mutation, so there is this certain level of susceptibility that you have to it, where you're more likely to have that than the population. I think people that don't have that genetic or that gene mutation, it's like 12% chance. So you can see it's a huge risk factor that's going up. So 12% to 45%. But what depends, or even 85%, but what it also depends on are the things you're exposed to or things you're not doing. So that's where the epigenetic part comes in. That's all the things you're exposed to. So, if someone has that, gene mutation, and then we'll just throw out a lot of different risk factors. Then they smoke, they're overweight, they're not getting sunlight, their circadian rhythm's off, they're exposed to a whole bunch of stress. Well, if you start adding in all these things, then the likelihood of that gene mutation being expressed starts to go up. And so that's why we want to do different things that might help to kind of bring that down. So making sure we're getting light exposure, we're getting good sleep, good circadian rhythm, we're exercising, we're in a normal weight pattern or weight distribution for us. So all those things play a role, kind of going along with that too. And so this can go along with the breast cancer is adipose tissue. So your fat cells actually will aromatize testosterone into estrogen. And again, we know breast cancers are sensitive to estrogen, so that means there's more estrogen floating around in your body. That means it could be more likely to get picked up by that breast cancer cell, and then that's going to increase growth. So again, it's this complex interplay of a lot of different things. It's not as simple as just this one thing or this one factor. But if we can keep our mitochondria healthy, then that can make a big difference. And that's why I think the cell danger response, that theory, can kind of help make a lot of sense out of a whole bunch of different disease processes going on, because it is kind of that one unifying factor. So hopefully you guys could follow this. Hopefully I was clear in everything. If not, please leave a comment. Let me know. I'll try to answer questions. All right, guys. So if you would, just please like, subscribe, leave a comment. That will just help to grow the channel, help get this information out there so I can help as many people as possible. And like I said, I would appreciate that. So I hope you guys take care. Have a great day, and I'll see you next time. Bye.